Hello everyone, I am Alper Tunga from Bahçeşehir University of Istanbul. My colleagues are Sena Kaçer and Burcu Tunga from Istanbul Technical University of Istanbul. Our study's title is HDMR-based image enlargement using Lagrange interpolation. So digital image enlargement is an important area covering image scaling, resizing, and interpolation in image processing. Actually, here we execute the enlargement process to make larger images by increasing their number of pixels. So it's basically an interpolation process, and some non-adaptive methods such as nearest neighbor, bilinear, and bicubic interpolation are used. So in this study, we focus on developing a new efficient digital image enlargement method using high dimensional model representation and Lagrange polynomials. So high dimensional model representation was first proposed by a Russian professor, Sobol, in 1993. After that, Herschel Rabitz from US and Metin Demirel from Turkey and their groups have worked on extending HTMR to solve different engineering problems. And nowadays there are many other groups in all over the world working on HTMR. So HTMR is based on a multivariate function decomposition philosophy, and we will use HTMR as a multivariate data partitioning technique in digital image enlargement. This is HTMR's expansion. It is composed of a finite number of summations. This is a finite expansion. And the right-hand side components are composed of a constant term, univariate terms, bivariate terms, and so on. To uniquely determine these right-hand side components, we define some vanishing conditions, which are also orthogonality conditions on the HTMR components. And these vanishing conditions are defined under a weight function, which is a product type weight. And we also define some normalization conditions in order to simplify the general structures of these HTMR components. To determine the HTMR components, we define some operators. This is the constant operator. It is an n-tuple integration. Here, this capital F function is a square integrable function. And when we apply this operator to the both sides of the HTMR expansion, we get the relation given in 6 for the constant HTMR term. And in a similar way, we define another operator to determine the univariate HTMR terms. This time we discard one integrand from the n-tuple integration in order to get the general structure of the univariate HTMR terms, which is given in number 8. We can find the other HTMR terms in a similar way. So in this study, our aim is to use HTMR as a multivariate data partitioning technique. To do this, we need to select a specific weight function. In this sense, we choose this one. So it's a Dirac delta type function. And here the alpha parameters are used to give a different importance to each node of the data set, and psi values are the data points of the considered problem. So when we use this weight function, Dirac delta type weight, we can rewrite the HTMR components for data partitioning as they are given in 10, 11, and 12. So here you see the constant term. We have the function values at the data points of the considered problem here. And we have n-tuple summation in constant term, n minus 1 tuple summation in univariate terms, and n minus 2 tuple summation in bivariate terms. And so let's consider these HTMR components in image processing. When we deal with the digital images, we get a matrix for representing each image, and that matrix has pixel values, and the locations are the x and y coordinates on the matrix. So here, the first dimension in this function is a row vector, which is corresponding to the values at x coordinate. The second dimension is a column vector, and these values are the values of y coordinate. And the last dimension is for the red, green, blue layers. So it can take on only three different values. And this f function is corresponding to pixel values at the locations. So when we apply this philosophy to the HTML components, we get this constant HTML term, these univariate terms, each demonstrates a one-dimensional array, and these bivariate terms, and here each bivariate term demonstrates a two-dimensional array. So this means that we decompose the given multivariate data set into univariate and bivariate data sets. To represent the considered image, we need to construct analytical structures to those partitioned data sets. To do this, we use Lagrange polynomials. So here you see in equation 16, we define the Lagrange polynomials. It's a routine, you know. And when we get these Lagrange polynomials, and when we have the HTML components, then we can define these multinomials in order to get the analytical structure for each partitioned data set. So when we insert these multinomials into the HTML expansion and cut the expansion at that level, we get the HTML approximates. So if we use only the univariate constant and the univariate HTML terms, then we get this univariate HTML approximate. And when we also, in addition to this, we also use the bivariate terms, then we get this bivariate HTML approximate. And in this study, we will use this approximate to represent both grayscale and color digital images. So what we are doing in digital image enlargement using HTML and Lagrange polynomials is we apply the HTML-based algorithm on both grayscale and color digital images. So you know, a grayscale digital image can be considered as a two-dimensional matrix, and it is represented by this matrix AI. Here x is the x coordinate and y is the y coordinate, and the elements of this matrix are the pixel values. So in our algorithm, we duplicate the image in order to increase the dimension of this matrix to be able to use the bivariate HTML approximation. So in this sense, this Z can take on 1 and 2, the values 1 and 2, because it's the duplication of the image. We represent the image through HTML with the help of Lagrange interpolation, and the degree of the obtained polynomial dramatically increases as the size of the image increases. So this also results in high computation and time complexities. To overcome this problem, we divide the matrix of the image into small submatrices. So, in summary, let me give you the steps of our algorithm. When we apply HTML to the grayscale images, we duplicate the image at first. Then we divide the matrix into 3 by 3 submatrices. Each submatrix is called kernel matrix. And you see here the general structure of this each kernel matrix. And then we apply our algorithm, our HTML algorithm, to each kernel matrix and evaluate the HTML components obtained for image processing. And after that, we obtain the Lagrange polynomials and construct the bivariate HTML approximant for each kernel matrix. So we have many kernel matrices to represent the original image. And when we construct the bivariate HTML approximant, then it means that we have an analytical structure representing each kernel matrix separately. After that, so our main idea is to enlarge the image. So we enlarge each kernel matrix to 5 by 5 from 3 by 3. To do this, we define some midpoints. You see here the list of midpoints. And we use the bivariate HTML approximant in order to calculate all the pixel values at these points. So this will help us to enlarge each kernel matrix to 5 by 5. But we know that we still don't have a 6 by 6 image. So up to now, we couldn't double the dimension of the original image. In order to double the image, we extend each 5 by 5 matrix to a 6 by 6 matrix by adding one row to the lower bound and one column to the right bound. And then we have to evaluate the elements of the sixth column and sixth row of this extended kernel matrix. To do this, we use the fifth column of our current kernel matrix and the first column of the next kernel matrix. Because we have many kernel matrices, we need to combine them to enlarge the original matrix. When we are combining them, we add extra columns and rows between those kernel matrices, and those added columns and rows are calculated using the last column of the current kernel matrix and the first column of the next kernel matrix. And we use a weighted mean to do this. We multiply the last column of the current kernel matrix by 9, and we multiply the first column of the next kernel matrix by 1 and then get the weighted mean. We do this in this way because our observations show that it's better to choose the midpoint very close to the left point, not the right or center of the considered interval. So we use a very high weight for the left column in order to get the weighted average. Okay, so we use this philosophy for both added column and added row. And if we apply this step to all kernel matrices when we are combining them, we get the enlarged digital image at the end. And to apply the algorithm to the color images, we apply all these steps to the red, green, and blue layers separately. And after that, we combine all these three matrices as a three-dimensional matrix in the same order of the original red, green, blue layers. Okay, so it's the same, but we applied that algorithm 3 times because we have a color image and we have red, green, and blue layers. Okay, so these are our findings. So we use these 5 figures, and we make a comparison between our algorithm and the nearest neighbor, bilinear, bicubic interpolation, and Lanczos. So you see here the PSNR values, and the largest PSNR value means the better results. The results show that HTMR is better than the nearest neighborhood in all cases, but it's not better than the others. They are very close to each other. So Actually, this shows that we need some improvements in the algorithm. And here, this is our findings for color images. We use these 5 figures, and these are the PSNR values, and the results are same. HTML is better than the nearest neighbor, but very close to the other methods. Not better than them, but not worse than bilinear, bicubic, and Langsos. And these figures are given for making comparison between these methods. So actually these are very close, the performances of these methods are very close to each other. So if we talk about concluding remarks, we can say that we propose a hybrid algorithm composed of HTML and Lagrange interpolation. We used 5 grayscale and 5 color images to test the proposed algorithm. We are better than nearest neighbor, but very close to the other methods. So finally, we can say that we need to improve our algorithm to be the best as a future work. Thank you very much for listening to me.